Okay, so today I just want to announce to everyone that the exam will be 2 weeks from today. Okay, so next there's going to be a homework assignment posted tonight on Blackboard. It's going to be due Wednesday, and most likely we'll end up going over some of the answers to those questions next Wednesday, so that you can use that to prepare for the exam. Okay, so we'll have a sort of a review session next Wednesday, and we'll go over some of the homeworks. The homework that you just turned in, and we also some of the homework that you will be turning in next week. Okay, the following week is Monday. You will not have class. Okay, you can use that as a study day, and Wednesday will be the exam. The exam will be held here, and it will be during the regular class period, so 7:30 to 9:10. That's about how long the exam should be. During the exam, you will be allowed to have a calculator, no cell phones, just a plain calculator. You will be allowed to. I'll either provide the equations. I'll either provide all the equations you'll need, or I'll allow you to bring a page of notes front and back. Okay. Yeah, I'll let you guys know next Wednesday. Uh, I think graphing calculator is fine. Yeah, you can use it to check over some of the integrations. Any questions? Any questions before we begin today? Okay. So the topics for today is, we've been talking about Coulomb's law. We talked about how to calculate electric fields. We did that with discrete charges first. So this is Coulomb's law. All right, that tells you the electric field from a single point of charge. So we extended that idea to what happens if we have multiple point charges. So we found the electric field from single charges, then we did multiple discrete charges, and then we found the electric fields due to charge distributions. And when we're talking about charge distributions, there's usually three types of charge distributions. A charge density could be given to you in terms of volumetric charge density, rho v, surface charge density, rho s, or line charge density, rho l. For each one of these cases, if we want to find the electric field, we have to add up the contributions of charge, to each one of these charges in the volume, the surface, or the line. So we did one example where we had an infinitely long line of charge, if you remember that. An infinitely long line of charge, and we were asked to figure out what the electric field was at a certain distance away from that long line of charge. In your homework, you'll have a problem where you have an infinite disk of charge, an infinite sheet of charge with a surface charge density, and you're going to be asked to figure out what the electric field is there. And there'll be other types of problems like this that we have in the homework and the exams. All right. Now, one of the things that we learned last time in class was that sometimes these types of problems the integrals of it can be a little bit hairy. We found a shortcut using something called Gauss's law. So with Gauss's law, the first thing you have to do is select a Gaussian surface. And you should select a Gaussian surface such that the electric field is perpendicular everywhere on the surface, and the magnitude of the electric field is the same everywhere on the surface. Those are the two key criteria for applying Gauss's law. If this type of symmetry exists and you're able to use this, then the problem becomes a lot easier. So at the end of class last time, we found the electric field for an infinitely long wire. We did it using Gauss's law, and we found out that it was a lot quicker to do it that way, a lot easier. So in the problems that you'll have in your homework or your exam, you want to think about symmetry first. If you can draw a Gaussian surface and it has that type of symmetry, then most of the time you're better off using Gauss's law. You'll be able to solve it relatively easily. If you don't have symmetry, then you will need to use the regular, the integration approach, or adding up the individual contributions of charges in order to find the electric field at a given point. Does that make sense? Yeah, you can. We'll start off with an example today. I want to jump ahead to this. Move this down a little bit. This is part of the notes, but it'll be posted. It will be posted as part of the next segment of the electrostatics chapter. But last time I taught this course, I made up this flow chart because it really found that it helps students in solving these problems. So electrostatics problems can get pretty complex. We started off with electric field problems. Today we're going to do electrostatic potential problems, and then we'll get into electrical energy problems as well. So with electric fields, the first thing you have to ask yourself is, do you have discrete charges? If you have discrete charges, like individual charges, then you have to use Coulomb's law, in the discrete form of Coulomb's law, where you add up the individual contributions of each charge to the electric field. If you have a charge distribution, like the kinds of problems that we're doing right now, that's the second type of problem right here. Then, if there's symmetry, then apply Gauss's law, because it'll make the problem a lot easier. If you don't have symmetry, then you have to apply the charge distribution. You have to use the charge distribution formulas, depending on whether you have a line, volume, or surface charge. All right. The third approach, if you know what the electrostatic potential is, we haven't gotten to electrostatic potential is, but if you know what V is, then E can be found simply by this formula. E is the gradient of the electrostatic potential. Okay, so if you just remember this problem-solving flowchart, then you'll be good. Just remember these two things right now. Discrete charges, what do you do in the case of discrete charges? What do you do in the case of a charge distribution? All right, so let us go back here. Let's start off today by using Gauss's law to prove Coulomb's law. All right, so in other words, like everyone to try this problem, using Gauss's law, derive the formula for the electric field from a single point source. All right, so imagine that you have a single point source with charge Q right at the origin. And we're going to use Gauss's law to find the electric field at some distance away from that. Now the answer to this you already know. The formula for the electric field from a single point charge was given to you here, Coulomb's law. All right, so you already know what you're looking for, or what your end result is going to be. What I'd like you to do is use Gauss's law to prove Coulomb's law. So to start this problem, the first thing to do if you want to try to apply Gauss's law, you have to look for symmetry, and you have to define a Gaussian surface. So if we do this problem, if I give you some hints right now, what are the things that we want to have in the Gaussian surface? What are the two criteria of the Gaussian surface? Yep. Mm-hmm. Yeah, the electric field should be same everywhere on the surface, right? It should be equal in magnitude everywhere on the surface, and the electric field should be perpendicular to the surface. It could also be tangential. Tangential fields will mean zero cross product. So either perpendicular or tangential to the surface. In this case, it would have to be a curved surface, absolutely. So when you're drawing your Gaussian plane, those are the two criteria. But if it wasn't clear from before, the Gaussian surface must enclose the charge. All right, so here we're talking about a point charge. In Monday's example, we had an infinite line of charge. So we drew, in the case of the infinite line of charge, what was our Gaussian surface? What did it look like? It was a cylinder. Right, right. Yeah. What type of surface could we draw around that charge that would be, where the field would be equal everywhere? Yeah, exactly. A sphere. The Gaussian surface will be a sphere. So knowing that, see if you can apply Gauss's law using a Gaussian surface of a sphere. Yep. You will be using spherical coordinates in this problem. All right, just to remind everyone, this is what Gauss's law is. And this is the form of the Gauss's law that you're going to use. All right, any thoughts on how to solve this problem? Yep, yep. You want to have a little bit more time? Sure. Yeah, no problem, no problem. All right, I'll be right back. I'm just. All right, thoughts? Let's write down Gauss's law first. E dot ds equals q over epsilon. All right, so this is Gauss's law. It must be a closed surface. So let's remind ourselves the Gaussian surface has to meet a few criteria here. The Gaussian surface must enclose the charge. All right, the second one, it must be E must be orthogonal to surface. Magnitude of E same on the surface. Say uniform. All right, so if you have a point charge, what type of surface will give you a uniform electric field? Okay, glad we know that. A sphere. All right, now, so we're going to take a sphere of radius, let's call it radius A, and we're going to do this integral here. Yep. Sure. That's fine. Yeah. We could do it with R2, but I'm just putting A here just to not confuse it with the integration variable R, or the spherical coordinate variable R. All right, so we want to do this integral here, E dot ds. So what is ds in this case? Okay. It's going to be R hat Yep, r squared sine theta d theta d phi. Got it. Okay, so that describes the area of a small patch on the spherical surface. The r hat vector points away from it, so it's the ds. Remember, the r hat vector always points perpendicular to the surface of the sphere. All right, so that's what ds is. And the electric field. The electric field is equal to, what direction is the electric field going to point? This is where we're taking advantage of the symmetry here. We have to have an intuition of the electric field. It's going to point in the direction of r hat. Yeah, we've seen this problem obviously many times before, and the electric field we know is going to point away from the middle of the sphere, right? The electric field points away from the charge. So when we defined our Gaussian surface, we decided a cylinder will be a good idea because everywhere on the surface, the electric field lines are perpendicular to it, and the magnitude is the same everywhere on the surface. So what we can do is we can define, we know our electric field is going to be in the r hat direction, and we can just call it E sub r. We're going to be solving for this. This is what we're going to be solving for. And we know there's no phi hat component. We know that from the symmetry. That's the intuition part. Okay. In this case, the intuition part is quite straightforward, right? Because it's just, you can't get anything simpler than just a one charge, right? In the case of a line, we drew our Gaussian surface was a cylinder because everywhere on the surface of the cylinder, the field was the same. Yes, Charles. ER is the radial electric field. Yeah. That's what we're going to solve for. All right, so we take the double integral of this on the surface of the sphere, E dot ds, so r hat times E sub r dotted with r hat r squared sine theta d theta d phi. That's r squared. And this is equal to q over epsilon. So when we do this dot product, we get ER times r squared sine theta d theta d phi equals to q over epsilon. Let's not forget the two integrals here. What's going to be our limits of integration here? All right, so theta is going from 0 to pi, and phi is going from 0 to 2 pi. All right. Now, if you look at your integral here, I'm going to show you a little bit of a shortcut. Right? You see that none of this stuff depends on the variable of integration. This one, these are all the thetas, and then these are all the phis, right? So we have a situation here where the variables are separated. This one is a constant. It's considered a constant because we're integrating with respect to theta and phi. All right, then we have this sine of theta d phi term, and then a d theta term, and then the d phi term here. So we can separate them. So we can make this a constant, ER times r squared. We can do our phi integration here. Phi is equal to 0 to 2 pi d phi. And then theta equals 0 to pi of sine of theta d theta equals q over epsilon. Right. Er times r squared. This just becomes 2 pi. And how about this one? Sine of theta. What's the integral of that? Okay, negative cosine of theta from 0 to pi equal to q over epsilon. All right, and this one is what? This comes out to 2. 1 plus 1. All right, so this comes out to 4 pi r squared. And remember, this r, we're at a fixed r, right? And that radius, the radius that we're at r is equal to a, variable a. So we can substitute that in here, 4 pi a squared times E sub r is equal to q over epsilon. So your electric field then is q over 4 pi a squared epsilon. And this matches Coulomb's law. Any questions there? Okay. Now let me go back and show you an even shorter way of doing this. Let me copy this. Q over epsilon, double integral of E dot ds equals Q over epsilon. All right, and we got all right. You have to know when to apply this shortcut, but let's think about what we have here. We have two vectors, ds and E are in the same direction. They're parallel to each other. So E dot ds is just equal to the magnitude of E times the magnitude of ds. All right. Why is that? If the vectors are in the same direction, remember when you take the cross product of two vectors, if they're in the same direction, then you basically multiply their magnitudes. Yeah, the dot product. Did I say cross product? When you take the dot product of two parallel vectors, you're just multiplying their magnitudes. All right, that's one of the shortcuts. Is when we take a Gaussian surface here, if E is perpendicular to the surface, then this E dot ds business becomes very simple. It's just the magnitude of E times the magnitude of ds. Right here. Now, we're taking the integral of the electric field on this sphere. The magnitude of the electric field is equal everywhere along that sphere. So the shortcut here is that the surface integral is simply the magnitude of the electric field times the surface area. Does that make sense? If we take this and we solve here, what did we find here? We found that this was equal to 4 pi a squared times ER. What's 4 pi a squared? It's the surface area of a sphere. This equation here, describes total flux. What is total flux? It's adding up all the electric fields everywhere on the surface. So if we're adding up all the electric fields everywhere on the surface, that's the same thing as multiplying the electric field times the surface area. Right? If the electric field is uniform everywhere on the surface, then you can just multiply the electric field by the surface area. So this E dot ds term is just equal to ER times the surface area. Is equal to Q over epsilon. All right, this is where we get our ER 4 pi a squared is equal to Q over epsilon, and then your electric field is equal to Q over 4 pi a squared epsilon. Same result, just a little bit quicker calculation. Any questions on that? Just to make sure that we're all totally on the same page with this, let's go back to our example from last time. All right, suppose we have an infinite line of charge. Let's redo this problem again. Sometimes it's helpful to look at the problem again. All right, we have an infinite line of charge. So let's draw an arrow that's just showing that we're going that way. And we have a bunch of positive charges here like this. Let's apply the same technique again. A Gaussian surface. Okay, we define a Gaussian surface. The Gaussian surface must enclose the charge. The electric field should be perpendicular to the surface, and the magnitude of the electric field should be the same everywhere on the surface. All right, we discussed this and we said, well, if you have an infinite line of charge, your electric field lines look like this. All right, they go away from the charge. So the surface that you can draw around here where the electric field lines are not only perpendicular to the surface, but they're also equal in magnitude everywhere, is a cylinder. Right? And every point on the surface of the cylinder, the magnitude of the electric field is E sub r. Now applying our shortcut again. So Q over epsilon is equal to the surface integral of E dot ds. All right, this E dot ds is going to be equal to E sub r times the surface area. What is the surface area in this case? So we have a cylinder of height h. The surface area is equal to 2 pi r h. Right? We're taking the surface area of the outside part of the cylinder, not the top and bottom, just the outside part. Now you might ask, well, why can we do that? It looks like it's an enclosed. It should be an enclosed surface, right? Well, when you have an infinitely long cylinder, then the surface integral on the outside of it is going to be much larger than the integrals on the top and the bottom of the sphere, right? So those become negligible. All right, so E sub r times the surface area E sub r times 2 pi RH. Now h is the height of this cylinder, and h is basically going to infinity. The total charge inside that cylinder that we drew, the total charge is equal to rho L times h, right? Because rho L is given in coulombs per meter, and we're basically summing up all the charge along that z-axis. It's just the charge density times the length of the wire. So that's why we get rho L times h divided by epsilon here. All right, the h's cancel, and then you get E sub r equals rho L over 2 pi r epsilon. So that was for an infinitely long line. The problem that you're going to have in your homework is going to be a disk. An infinitely large disk of charge. You're going to find the electric field at some point A away from that disk of charge. Yeah, that's it. This is the XY plane. That's correct. The XY plane. This is the Z. I'm nodding my head. I'm not saying yes. No. Yeah. You will. You will. So you're actually going to solve for this both ways. You're going to do the charge integration approach, and you're going to do Gauss's law approach, and you should get the same answer both ways. All right. Good. So, any questions on Gauss's law then? All right. Let's do one more example today. We are going to do another example of electric fields due to calculating electric fields by a charge distribution. We're going to do another line integral today, but keep in mind that these problems are not all going to be line integrals. In fact, your homework problem that I just mentioned is going to be a surface integral. But let's do another line integral problem right now, also in cylindrical coordinates. Suppose we have a ring with charge density rho L in coulombs per meter. And this is a ring. So imagine a wire with rho L coulombs per meter charge density on it, and that wire is wrapped into a ring like this. And that ring is on the XY plane. And we are at a point 0, 0, H away from there. So we're on the Z-axis at some location H. What's going to be the electric field at this point H? All right, so how do we solve this problem? We have two options, right? If we're given a charge distribution, we can either use Gauss's law or we can use a charge integration. So, can we use Gauss's law in this problem? I heard no's from people. Why can't we use Gauss's law in this problem? Yeah, we can't get a surface where the field is uniform. So let me just rephrase what you say. We can't draw a surface on here where the field is going to be the same everywhere. The symmetry just isn't there. Yeah. Ah. Yeah, that's a good thought. If this line were in one dimension. This is exactly along the lines I want you all to be thinking, right? Thinking about Gaussian surfaces. Justine brought up a very, very good point. Like in the previous problem where we had this infinitely long line of charge, we drew a cylinder. Our Gaussian surface was a cylinder around that line, right? Justine's asking, why couldn't we do the same here? You know, you could imagine a cylinder that's drawn around this ring, like a cylinder wrapped or that goes around the wire. So it forms a torus, like a donut shape, right? What we would find is that the electric field on the inside of the torus would be different than the electric field on the outside of the torus. So one of the things we had to do with Gauss's law is that the electric field has to be uniform everywhere on the surface, everywhere on the surface. Good point. All right, so we can't use Gauss's law. We established that. So let's try to find the electric field intensity on the z-axis by charge integration. The more practice we do, the better off we are. So everyone, please try this problem. Give it a shot. We did an example last time with charge integration. Let's try another one now. And it'll make your homework easier the more practice you do. DL, that's a very good question. Which one of these equations are we going to be using in this case? The last one, of course. The question is, what is the DL? DL is what we're integrating across, right? If we want to go around this ring, what's going to be the variable that we integrate? Yeah, but what's the variable? The limit is 0 to 2 pi, that's correct. What's the variable that we integrate? Phi. What is the corresponding differential length element? What is the differential length element corresponding to a change in phi? R d phi. Yeah. So whenever you're integrating with respect to phi, what's the differential length element when you change phi? Right. These are something that it will be helpful to you if you just memorize it. So let's just touch on that again. If you're in the Cartesian coordinate system, very easy, right? Change in x, change in y, change in z is just dx, dy, dz, right? In cylindrical coordinates, if you have a change in r, it's dr. If you have a change in phi, it's r d phi. The differential length element is r d phi. How about z? Just dz. All right, now real quickly, how about cylindrical? How about spherical coordinates? If you have a change in radius, what's the differential length element? Tr. Change in theta. Nope. Rd theta. Change in theta. Theta is the vertical is the vertical one. All right. That's Rd theta. And how about phi? R sine theta d phi. Yeah. Memorize those. It will really make your life easier. Yep. Good. Yeah. If you're trying to visualize it, then look at this thing here. You're going around a circle, right? So this differential length element is kind of like the arc length of a circle, right? So that's why you have to multiply the change in angle by the radius. Hmm? It's like yeah, you're right, absolutely. Like the larger your r is, the larger your arc length is going to be. That's why you have to, yeah. I'm sorry. The rho, you mean the charge density? Well, you're given it in symbolically. It's rho L. Hmm. So here's the equation. Rho L divided by 2r epsilon as the electric field as the final solution. Not quite. It's actually a little bit more complicated than that one. The lateral fields will cancel out, but the z field may not necessarily cancel out. Oh yeah, 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 yeah. That's right. That's right. Sorry, my mistake. Hmm. All right, everyone, give it an attempt. Where are we stuck? Are we stuck anywhere? Sure. Yep. Electric field from a ring of charge. All right, let's before we start doing the math, let's think a little bit about the symmetry of this problem. Electric field lines always point away from positive charges, right? So the electric field lines are going to be pointing away in this direction, away in this direction. If you have the electric field, if we're looking at a certain observation point P, which is some height away from it, what we're doing in these formulas is that we are essentially adding up the contributions of each charge on that line. So you can imagine that if this is our observation point, and we are looking at this charge. Let's say we are looking at this point of the ring. and there's a positive charge there, so the electric field points from the charge towards the observation point. All right, and that generates an electric field. The direction of the electric field is basically an extension of the vector that connects the two. All right, so you draw a line from here to the point, and the electric field will continue to point away from that line. It'll be parallel to that vector. What this graph is, or the image is trying to show you here, is that there is some amount of symmetry, and the lateral components will end up canceling. Why will the lateral components end up canceling? And you'll be left with just a z component. Exactly. At every point on the surface, so you imagine if we're talking about this portion of the circle, this portion of the ring, this generates a field in this direction, while directly across the ring, there is that the charge on that side generates a field that is pointed in the mirror image of this. Right? So when you add up those fields, just like we did in the problem last time, the lateral fields end up canceling, and you're left with just a z component. I can draw on here. Everyone can see this, like the electric field from the resulting from the opposite side. Absolutely. Yeah, that's why I'm just redrawing it here, just to make sure that I know this is most people already get this, but it's worth it to me too. So let's say we're talking about this charge component here. The electric field lines resulting from here points in this direction, but on the opposite side of the circle, there's also a charge that creates an electric field in this direction. So this is E1, and then this is E2. The lateral components of the electric field cancel. Right, this E1 is equal to something like this. The E2 is equal to something like this. So the radial components, this is negative R, and then this is R. The radial components will cancel, and you're left with just the Z components of the field. So the total electric field along the Z axis is going to end up being in just the Z direction. All right, so that's a little bit about the symmetry of the problem. Now, to solve the problem, just use this. E equals 1 over 4 pi epsilon. E equals 1 over 4 pi epsilon, the integral of r hat over r squared, rho L. Okay. Now, if you remember from our discussions with Coulomb's law, 4 pi epsilon r hat is equal to r divided by the magnitude of r, right? That's the unit vector in the r direction. So we're going to rewrite this as r over rho L dl over magnitude of r cubed. Both forms of this equation is fine, equally valid. All right, so now we're getting into the geometry of the problem. So let's say we have an observation point, and the length of this leg is h, because that observation point is a distance of h away from the xy axis, the xy plane rather. the radius of the disk is b. So when we approach these types of problems, we want to figure out what r hat is and what the magnitude of that is. We also want to figure out what rho L dl is. And so with Ali, we just, Ali brought up the points like what do we integrate in this problem? What is dl? We said we're going to be integrating around the circle, so we know that dl is r times d phi. And the limits of integration for phi are going to be from 0 to 2 pi. So we've already figured out a part of the problem, but we also need to figure out what this part is. What is r, and what is the magnitude of r? All right, so r is the vector that points from the charge. So the charge is here, and this is the observation point. So r points in this direction. It points from the charge that you're integrating to the observation point. All right. So we're doing this problem in cylindrical coordinates. So what is that vector going to be equal to? R is equal to, so we are going inwards and up, right? So we're going from r equals b to r equals 0. So it's negative b times r hat and what's the second part of the vector going to be? Plus h times z hat. Yeah, so from this point here, from the location of the charge, I'm going from r equals b to r equals 0. So the movement is negative b. And then you're going up in z. R is the vector that points from the charge to the observation point. That's what this R defines. Yeah, we don't want to get confused with variables. Make sure we make sure you know that the R in this case is a vector that points from the charge to the observation point. What's another way we could find this? I just want to remind you that the way that you find the R is you subtract the locations of the points. So this is the observation point P, and this is the charge Q. Right? So P, what's the coordinates for P? 0, 0, H. And the coordinates for Q? B, 0, 0. And P minus Q. R is going to be equal to P minus Q. So that's going to be negative B, 0, H. Right, which is the same thing as what we found here. All right, so we found our R. And the next thing we do is we put this R into the formula, 4 pi epsilon. So negative B times R hat plus H times Z hat over the magnitude of R cubed. So if this is R, what's the magnitude of R? Square root of B squared plus H squared. right? You can see that from Pythagorean's theorem here by the triangle. Yes? R is a vector. That's right. That's right. So this is just a, you remember, it's good. I'm glad you asked these questions because they're probably things that other students are wondering as well. When we were generalizing Coulomb's law, the way to find that vector between P and Q was just to subtract the coordinates of Q from the coordinates of P. And that works in any coordinate system. All right. Then dl is r times d phi, and then we defined our limits of integration. Phi equals 0 all the way around the circle. Phi is equal to 2 pi. All right. Now again, I will just like we did in the problem last time with the infinite line of charge, we can use symmetry to make this math a little bit easier. Which term can we cancel out in this problem? We can cancel out the r hat term. Why can we cancel out the r hat term? Correct. We know that this r field, the lateral field, is going to cancel, and you're going to be left with just a z field in the end. Yeah. Mm-hmm. Oh, it is going to be b. Yeah. Thank you for mentioning that. You're correct. Right. The radius. We are at a constant radius in this problem, right? So this radius is going to be equal to b. Equals b. Did I not put that in there? Oh, yes. Okay. Thank you. Yep. Rho L. This one should be cubed. Yes. Thank you very much. See, everyone, this is great. Thank you, Justine. This one, the bottom of it's cubed, right? The magnitude of r cubed. So we're going to make this to the power of 3/2. Thank you for that. Now our equation is looking more correct. We took the rho L and we moved it outside here because it's a constant. We have this r d phi here, and that the radius is just going to be equal to b because we're at a constant radius. We're integrating around this ring of constant radius. And this r cubed term, so r, the magnitude of r is equal to the square root of b squared plus h squared, which is, b squared plus h squared to the 1/2. And we're cubing that. That's why we get 3/2 in the denominator. And then finally, like we said, that r hat term is going to 0. There's only going to be a field in the z direction, so we're not even going to bother calculating that. All right. So now what do we do? How do we solve this integration problem? Yeah, so this particular problem, we don't even need to look it up in the integral table because what the form that you have here is you have u to the 3/2, and then you have du at the top. So I'll show you what I mean. So let's say on your denominator, you have u is equal to b squared plus h squared. So du is going to be equal to 2h. Yes? Oh, thank you. See, you guys are smarter than I am. Oh. I'm glad. I'd rather have it that way. Yes, I'm overcomplicating. Look at this problem. There's no 5 variable in there. My mind is still thinking about the other problem where we had to do that integration. So thank you. Thank you. Good. Rho L times 4 pi epsilon times 2 pi times B times H times Z hat over B squared plus H squared to 3/2. 2 pi's cancel with 4 pi, left with 2 at the bottom, and you're left with rho L times B over 2 pi epsilon H. I'm sorry? Q rho L over 2 epsilon H over B squared plus H squared to the 3/2. All right. So that is our electric field, and it's pointed in the Z hat direction. All right, thank you for corrections. You treated R hat as 1, like this one here. You're talking about this R hat, this one. Yeah, that one, that R hat has to point from the location of charge to the observation point. That's really the most tricky part of that problem, finding that R. After that, it's just math. It's the location of the observation point P minus the location of the location of the charge Q. The direction points from Q to P. Final minus initial. Okay. So what does this mean? The electric field basically becomes 0. Well, yeah, it becomes 0 at Z equals 0. So H is the distance between this point and the XY plane. So Isaac brought this point up earlier. And I'd like you'll think about it. Why would the electric field become 0 when you get to the middle of the ring? And this equation is telling us that the electric field lines will become 0 when we get to the middle of the ring. Yeah, right. Exactly. The same thing as the lateral fields. So let me bring up another thing, since we're all thinking along these lines now. Let's say I have a cylinder of charge like this, okay? And that cylinder of charge, the cylinder, like imagine like a hollow cylinder, okay, a tube, and it's a metal tube, and that metal tube has charge on it. What's going to be the electric field at the middle of that tube? So let's say you have this tube, right? And this tube has rho s. It has a charge density associated with it. The question is, what's going to be the electric field right in the middle of that tube? The center. Like we're talking about, like in the center here, like right in the middle of the. It'll be 0 if you get the center point. Why? Why is that? Well, it's very similar to the problem that we have here. We have, if we look at the cross section of the wire, you have a bunch of charges like this, and you're looking right at the middle here. That's a good question. We're going to talk a little bit more about that when we start talking about metals. But if you have like, if the interior is a metal, then like that would be a case where you don't have any electric field. You don't have any electric field anywhere in the interior. But the dielectric, slightly different story. Okay. And that's actually one of the reasons why you have coaxial cables. You know, you guys know that when you do these experiments in the electronics lab, you have coax cables. And the structure of a coax cable looks something like this, where you have a conductor on the inside. I should say you actually have you have one conductor that's like this, and then you have another conductor that's on the outside like this. All right, we're going to be talking more about what the coax cable is like later on, but one of the functions of it is that the outside of the coax cable is grounded, and so that by having this coaxial shape, it actually helps isolate some of the interior of the coax cable from outside electromagnetic interference. So it's better for if you're trying to do low noise detection. And part of the reason is because you have these situations where the electric fields can, influences from the outside can actually cancel on the inside. We'll talk more about that later, but I just want to mention it right now since we're talking about, you know, field symmetries and things like that. Okay. Oh, wow. Let's now talk about potential energy. All right, we're going to now talk about electrostatic potential. So when we get into electrostatic potential, it's worth it to talk about what potential energy is, because voltage, it's called electrostatic potential, and it's a way to describe potential energy in the electrical domain. So before we get into the electrostatic potential, why don't we just define what potential energy is first? If you have a mechanical system or an electrical system, you know, what is the potential energy? In a mechanical system, you guys did this in physics, right? You throw a ball into the air. When you throw a ball into the air, the tennis ball has potential energy. What type of potential energy is that? Because you're dropping the tennis ball, let's say. What does that potential energy due to? Gravity. It's gravitational potential energy, right? So imagine we're just dropping the ball from here. That gravitational potential energy is being converted to what? Kinetic energy. By the time the ball hits the ground, the gravitational potential energy has been converted into kinetic energy. So that's a mechanical domain. In the electrical domain, what we imagine is a charge between the positive and negative plates of a capacitor. So, imagine that you have two plates like this, and you apply a voltage between them, your classic capacitor. Right, you end up getting positive charges on this plate and negative charges on this plate. Right, now, this is a similar type situation. Let's say we put a positive charge here. What direction is the electric field? Away from positive towards the negative, right? So this is your electric field. What's the force on that particle? It's going to move it from positive charge to negative charge, right? So as this particle moves, it actually gains speed. Just like if you drop the tennis ball, it gains speed as it's going down. So this is an analogous concept as when you drop that tennis ball. In the case of the tennis ball, the gravitational potential energy was converted into kinetic energy. And in the case of this, the electrostatic potential energy is being converted into kinetic energy. All right, we'll get into the definition of that in just a second. All right, before we do that, it's just worth it to let's talk about the mechanical potential energy and some of the calculations that we did with it, because we're going to be doing the same things in the electrical domain. So we understand that a charge in an electric field has electrical potential energy. How do we quantify it? So in mechanics, what we do is we define the potential energy as the amount of work it took to put that tennis ball at some height in air. And we're going to use a similar approach in electrical systems. So in the mechanical energy, what is the potential energy of a tennis ball? The tennis ball with a mass m at a distance h from the ground. So this is where I'm holding the tennis ball before I let go. So there's going to be a force in the downwards direction. It's at a height h. So what I'm doing here is what we're going to do in the electrical domain as well. I'm going to calculate the work that it would have taken to put this tennis ball up in the air like that. Work is equal to the force times the distance. You guys remember this from physics. Work equals force times distance. The differential work is equal to the force times the differential distance. What that means is that if we were going to break this up into small chunks of height, so if this was like 10 meters, then we break this up into 10 different segments, and we say how much work was done to move it from here to here, how much work was done to move it from here to here, and so on until we add up those contributions until we get the total work. So this differential work is equal to the force times dx. The total work required to get this tennis ball from here to here is equal to the integral of force times dx. It's an integration. And you're integrating it from this x equals 0 to x equals h. This x is the height coordinate here. You integrate f times dx from 0 to h. The force at any given point is constant. It's equal to mg. Force is equal to mass times acceleration. So that's where this mg comes from. G is the gravitational constant, 9.8 meters per second squared. All right, you integrate a constant with respect to x, so this can be taken out of the integral. You're left with just the integral from 0 to h of dx, which gives you h. And so the work required to get this tennis ball up there was mass times the gravitational constant times h. This is the definition of gravitational potential energy. The amount of work that it took to put this tennis ball up there is the amount of gravitational potential energy that tennis ball now has. M is the mass. Yes. The mass of the tennis ball. G is the gravitational constant, 9.8 meters per second squared. and h is the height at which how much you moved it up. So with electric potential energy, there's an analogous concept. How much work do we need to do to move a charge in the presence of an electric field? So let's say you have an electric field that looks like this, these blue lines here, and the force on this charge is going to be in the same direction as the electric field. Remember, if you put a positive charge in an electric field, the force on that charge is going to be in the same direction as the electric field. Right? You can think about the electric field exerts a force on that particle. So the force is going to be in this direction, okay? Now, if we want to, this is similar to gravity. Gravity is exerting a force on this tennis ball, and that's causing that tennis ball to drop. In this case, the electric field is exerting a force on the particle, causing it to move in this direction. Same idea. In the mechanical analogy, what we were doing is we were moving against gravity. So as we lift the tennis ball up, we're exerting a force against gravity. In the electrical analogy, we are, imagine grabbing this little charge and moving it against the electric field. Same idea. So that's what this force external is. Imagine moving this charge against the electric field, and by doing that, the charge is gaining some potential energy. Just like moving the tennis ball against gravity is giving it some gravitational potential energy. So this external force is equal to Q times epsilon. In the mechanical domain, the force is equal to m times a, mass times acceleration. In the electrical domain, this force is equal to Q, the amount of charge, times the magnitude of the electric field. The amount of work that we did, if we moved this charge Q, we grabbed it and we moved it by an amount equal to dl, the work that's done, dW, is equal to force times dl. And that force was the electric force, so it's equal to negative Q times epsilon times dl. Just a small note here, the negative is because we are moving it against the electric field. So just like we define gravitational potential energy, we're now going to define something called electrostatic potential. Electrostatic potential is the work per unit charge. Why do we define it that way? The more charge we have here, the more force it's going to take to move it against the field, right? Just like if you have a bowling ball versus a tennis ball. The heavier that ball is, the more force you have to exert to move it against the force of gravity. Similarly, if you have a larger charge, it's going to take more force to move that charge against the electric field. So that's why electrostatic potential is defined as work per unit charge. The units are joules per coulomb. In other words, volt. 1 volt is a joule per coulomb. The total potential found by integrating, just as we did with mechanics. So dV, V is the voltage, the electrostatic potential, is equal to work per unit charge, dW divided by Q. And that's equal to negative E times dL, just from this equation here. Right? We define dV is equal to dW divided by Q, and from this equation, it's just negative E times dL. This is the differential form of the electrostatic potential. You integrate both sides of the equation. You integrate dV, you get V. You integrate negative E dot dL, and that's what this is here. This is just a vector form of it. Right? And you're integrating this along a line. The line is the line that traces how you move that particle through the field. It could be a straight line if you moved it straight up. against the field. It could be a curvy line if you move that charge in a curvy fashion. So this is the integral form, and the differential form is E is equal to the gradient of V. So if you were to take like a vector differentiation of this side and a vector differentiation on this side, you essentially get the same thing. All right, so E is equal to negative gradient of V. We'll be doing some examples of that. You can plot V. If you're given a potential field, it's very easy to plot the electric fields from that.
That's E in the differential form. Is that still epsilon?
This is just E. There's no epsilon here. This one?
Yeah,
This one here? No, there's no epsilon here.
No, is that epsilon or is that just E?
It's just E.
Okay.
Just E. Yeah. Good question. Yeah.
You said that specific, you could have different potential at the same point with the same charge depending on path?
No. No. Electric fields are conservative, so regardless of what path you choose. I was just making the point here is that DL doesn't necessarily have to be a straight line. It could be any path. So electric potential, the physical meaning. Electric potential is related to the work done when carrying a charge from one point to another. The difference in potential V2 minus V1 is the work required to move a charge from P1 to P2. So in this formula, which we'll probably start with next time since, there's a couple problems in your homework that require you to calculate potential. So we'll go over this Monday, and you'll have, I guess, a couple days to do it. But you can look ahead if you'd like. The difference in potential V2 minus V1 is the work required to move a charge from P1 to P2. So notice that in this formula for V2 minus V1, we can take any path we choose, which is the point that you were getting at. So let's suppose we had a charge at this location, and this is what the electric field looked like. If we take this charge and we move it from P1 to P2, there's a certain amount of work that was required to move it in that direction. We're moving it against the field, you can see here. So P2 is going to have a higher potential than P1. The way you calculate the difference is that V2 minus V1, the difference in potential, is the integral from P1 to P2 of E dot dl. And remember the negative sign there. So you imagine a line connecting P1 and P2, and you take the integral of E dot dl along that line. All right, so we spent time in the last chapter looking at line integrals, right? So the reason we spent time there is because you can see these line integrals are just coming back again. If you know how to do these line integrals, you feel comfortable with it, you know how to define DL, you know how to set the limits of integration, put everything in terms of a single variable so that you can do a one-dimensional integration, then you'll be in good shape to do this. So, since we're just about out of time here, I think that, just try doing this problem on your own before class on Monday, and you'll see that there's a problem in the homework that's very similar to this. Try it out, and then come on Monday with questions about this one and also about the homework. The homework will primarily cover electrostatics and Gauss's law. There will be a few problems on electrostatic potential and work. So we'll be covering the concepts of work covering the concepts of work on Monday. All right. So we'll leave it at that. The homework again will be posted tonight. Make sure you get a start on it this weekend. Try to finish as much of it as you can so that on Monday you can ask questions about it. It will be due next Wednesday, and we won't be able to do extensions on that because I want to make sure that we have the homeworks back for the test. All right. Thanks, everyone, for your attention. All right.